imperfect gas equation. That is, if we have pressure P of an imperfect gas, rho is density, K beta is Boltzmann's constant, and T is temperature, we know for perfect gas, the equation, simple equation is P is equal to rho K beta T. But the virial theorem tells the total kinetic energy, the mean of kinetic energy T, mean of kinetic energy T is minus half of mean of, or you can say expectation of sum over I Fi Ri. You can find if T is your kinetic energy term, then this is minus half times sum over Fi into Ri, where Fi represents force and Ri represents position vector. If you go to the virial theorem, you can find, let us consider a collection of gas molecules, and the position Ri represent the position vectors. So we define the momentum vector G as a quantity which is the scalar product of Pi dot Ri dot, and the summation extends from I to any particle. So dG by dt, when you differentiate these two terms, then this is sum over I Pi Ri plus sum over I Ri Pi dot. Then what it indicates? It indicates that the Newton's second law of motion, we can identify the RHS term, that is Pi into Ri dot is Fi into Ri. And the second term is Ri dot Pi, which can be written as Pi is MAI Ri, that is Ri dot into Ri, which can be written as MAI Ri dot is Vi into Ri dot Vi. So this is MAI Vi square, or we know kinetic energy T is half mv square. So this is MAI Vi square is equal to 2T, or T is equal to half MAI Vi square. So what will be this equation? dG by dt, which is equal to F dot Ri plus Ri Pi dot, that will be 2T Ri, this term is 2T plus sum over I Fi Ri. So if you take time average on both sides, gives dG by dt was 2T plus sum over I Fi Ri. If you take time average like expectation value symbol, this is 1 by tau for time average, integration 0 to tau dG by dt into dt, which is 2T expectation, that is your time average, plus time average of sum over I Fi Ri. When you evaluate the second integral, you can find this term, that is the LHS side term upon integration gives rise to 0 result. So 2T plus Fi Ri is equal to 0. That means T is equal to, since left hand side is 0, 2T is equal to minus Fi Ri, and T is equal to minus half sum over I time average of Fi Ri. So this theorem is called your virial theorem, that is time average of kinetic energy. Statement of virial theorem is time average of kinetic energy is minus half of time average of sum over all particles into scalar product of Fi into Ri, where Fi stands for the force acting on ith particles, Ri is their position vector, and this time average term is called virial calculus. This theorem is called virial theorem, and this time average called virial calculus. You can derive Boyle's law. You know Boyle's law, temperature constant P1 V1 is P2 V2. You can derive that one by using this virial equation. How you can derive? You know this for a continuous system, we can write the virial term, that is half sum over I Fi Ri can be written as half rho times integration over closed surface Ri ds. By using Gauss divergence theorem, we know double integration A dot ds is a triple integration. That means surface integral is converted to volume integral here. So Ri dot ds is a triple integration divergence Ri into dv. And upon integration, this term right hand side is 3 by 2 pv. So what is left hand term? Left hand term is nothing but your kinetic energy. So kinetic energy T is equal to 3 by 2 times PV. And if you consider m is mass of each particle and n is number of particles, then the total term T is equal to half 1/3 mn c RMS square. This represents your RMS velocity. So using these two terms, T is 3 by 2 PV, T is equal to this one. So PV is equal to, you can write 1/3 mn c square, which is nothing but c is root mean square velocity. So at constant temperature, PV is equal to constant, and T is constant, c square is constant, m is mass constant, n number of molecules constant. So PV is constant. This is nothing but your Boyle's law. Hence, the average kinetic energy of translation of a gas in steady state represents your virials. This indicates the average kinetic energy represents your virial state. So let us identify what are the forces which acts on the imperfect gas or real gas. What are the gases? First one is, what are the forces acting on imperfect gas? One is force of impact due to collision of molecules inside the container. Second one is force of collision between the molecules. Third one is intermolecular forces. Now, considering these forces into account, we can assume, let those gases present inside the container are monoatomic gases. So its partition function is represented by this. You know the partition function representation. It is Qn 1 by n factorial h to the power 3n double integration e to the power minus beta h dp1 dp2 up to dpn into df1 df2 df. What is beta? Beta was already discussed, 1 by k beta t. And the corresponding Hamiltonian in this case will be h is equal to 1 by 2m summation n varies from 1 to n pxn square plus pyn square. That means momentum along x, y and z direction. And plus, this is your kinetic energy term, p square by 2m in all directions for all particles, plus potential energy term, which is a function of x1, x2 to xn, y1, y2, y2 to yn, and z1, z to z. Hence, we can suggest that when you take the integration over the running index, and integration is performed over total number of molecules, the partition function becomes Zn is integration e to the power minus un by k beta t d r1 dr2 up to dr, such that for an ideal gas un is very negligible. So we can define this Qn, Zn is v to the power n, so Qn term will be 1 by n factorial 2 pi mk beta t by h square to the power 3n by 2 into v to the power n. Or in other words, we can write Qn as small q to the power n by m. What is qvt? Qvt is 2 pi mk beta t by h square t by 2 into v. And this represents that it is directly proportional to the perfect gas, or it represents the equation of state of a system. Hence, for real gases which obeys the van der Waals gas equation, they also statistical, if you consider their statistical behavior, we can calculate their partition function as well as we can calculate in monoatomic gas, we can prove Boyle's law and Charles' law and other laws. Now, the next heading is the Kamerlingh-Onnes equation. For Kamerlingh-Onnes equation, we have to consider the perfect gas equation, and it expresses the perfect gas equation, which is the infinite power of our density. So we define the term P by KT. This is Kamerlingh-Onnes equation. P by K beta T is rho. Here there is a term B1 rho. Here B1 is 1. I will tell what was B1, B2 and B3. B2 is a function of temperature into rho square. Rho plus a constant B2 T rho square plus B3 T rho Q plus so on. What are B1, B2, B3? B1, B2, B3 are virial coefficients, are three virial coefficients. Remember, Kamerlingh-Onnes equation suggests P by K beta T is rho plus B1 rho, B1 which is a function of temperature, its value is 1. So, first virial coefficient value is 1. Second virial coefficient B2T we have to evaluate. Third B3T we have to evaluate. So B1, B2 and B3 are called virial coefficients. Now we can rewrite this equation. When you take a rho, you divide this equation by rho. So P by K beta T rho, so rho square becomes rho Q becomes rho square. P by K beta T, you divide it by rho to both sides, then rho by rho is 1 plus beta 2 T rho plus beta 3 T rho square. And this clearly indicates that this P by K beta T rho is a term which indicates that the ith virial coefficients can be obtained in terms of interaction between ith number of molecules in a given volume V. So how can we derive this virial equation from grand partition function? Yesterday we know the grand partition function, which looks like the summation symbol V of T on mu, that is grand partition function, which is n varies from 0 to infinity, Qn which is a function of n Vt e to the power mu n k beta T. Qn is a function of n Vt, mu is chemical potential, n number of particles, k beta Boltzmann's constant, T is temperature. So the grand partition function we can write it Qn n Vt lambda to the power n. What is lambda? Lambda is e to the power beta mu, and beta is equal to 1 by kBt. What is mu? Mu is your chemical potential that is defined in your thermodynamics. Mu is 1 by n E plus Pv into Ts. So the average number of molecules, when you calculate for the single state of the system, the energy is 0 and Qn value becomes 1. So when Qn is 1, so this function reduces to grand partition function, becomes 1 plus Qn Vt lambda to the power n. And value of n is nothing but lambda times delta nz by delta lambda. So we get a density and the pressure in terms of grand partition function. This indicates the function can also be written as, this is Zn can be written as the grand partition function 1 plus Qn V to the power n by Q to the power n Z to the power n, and we define a quantity Zn as the V to the power n times V to the power n by Q1 into Qn, where defined by the configurational integral, and under these conditions, we get the Grant partition function is nothing but 1 plus Zn divided by L. So we can have large number of examples. We can work out large number of examples to obtain the virial coefficients, that is B1, B2 and B3. So all these three virial coefficients can be obtained from the Grant partition function. But we are limited with three virial coefficients, that is B1, B2, B3. B1 is 1 already known and we can derive it. So when we find three virial coefficients using Grant partition function, we consider that is rho, that is density, is number of particles by volume, and n value is lambda log delta log Grant partition function by del lambda. So z by v delta log Grant partition function by delta z, and that is nothing. So rho is equal to z by k beta t del rho by del z. But we have rho is equal to sum over j is infinity, j bj z to the power j. Bj represents our coefficients, virial coefficients. Hence, to determine these virial coefficients, we have to consider the equations, certain equations in a imperfect gases, and this gives the value that rho by k beta t is rho plus b2t plus rho square. From this equation, we derive this result that b2t is minus b2 2v to the power minus 1 z2 minus z1 square. Similarly, b3t is 2 minus 2b3 4b2 square, which is minus 1 by 2v square, v into z3 minus 3z to z1 2z1 cube minus 2 into z2 minus z1 square of whole square. Hence, you evaluate, take this expression, and you will find beta 2, which is second virial coefficient, takes the form 1 by 2v double integration exponential minus beta phi 1 2 minus 1 dqf1 minus dqf2. So the second virial theorem, which was evaluated in this form, leads to Lennard-Jones potential, or in short term known as LJP. To Lennard-Jones potential is a simple illustrative model which describes silent features of interatomic and intermolecular interaction. So what is Lennard-Jones potential by LJP indicates? Now it gives or it describes the silent features of interatomic and intermolecular interactions. So to derive this, we have to take the assumptions of the model. What was first assumption of Lennard-Jones potential? If we have atoms and molecules inside a system, the two, we assume, first assumption, two isolated particles would not be interacting when they are infinite distance apart. If two particles are infinite distance apart, they will not interact. First condition, if two particles are infinite distance apart, they will not interact. Second one, the Lennard-Jones potential always asked in the examination. So the interaction will be attractive if the particles are moderate distance. If particles are very minute distance apart, then the interactions will be attractive, and you will see the interaction varies inversely with the sixth power of interatomic separation, intermolecular separation. And you know from the solid state graph, similarly the repulsive interaction when the particles are very close to each other, when particle is in moderate distance apart, this interaction varies with 1 by r to the power 6. When the interaction is large distance, very close to each other, it varies with the 12th power. So this is the graph Lennard-Jones potential. You remember this is phi r, how it varies in this manner the Lennard-Jones potential varies, and that is according to the equation, this phi of r is equal to c some constant, that is sigma is your molecular diameter, such that this distance OA is equal to 2.16, 2 to the power 1 by 6 sigma. So phi r is equal to Lennard-Jones potential is C minus sigma by r to the power 6. That means it varies with 1 by r to the power 6, and this is the attractive term, and the repulsive interaction varies with 1 by r to the power 12. So on the equilibrium of separation R0, you can find this term, this phi dash r becomes equal to 0. So Lennard-Jones potential, which was expressed, so can be written as in the form phi r is 4 epsilon 0 minus sigma by r to the power 6 plus sigma by r to the power 12. If you use Lennard-Jones potential, then we can derive the second virial term, virial coefficient, that is V2T. The expansion is like this, 2 pi by 3 sigma 3 tau to the power minus 1.4, and the term in the bracket 1.733, so many terms, where tau represents k beta t divided by epsilon 0. When we are able to calculate this term, and this term beta 2t by beta 2t is second virial coefficient by sigma q, then it varies with the tau, the time, that is k beta t by epsilon 0 in this manner. That is behavior of second virial coefficient according to Lennard-Jones gas, and the variation shows the logs, the variation shows it increases up to this point, then it remains constant, but at larger distance it undergoes, which increase in temperature, it is slightly decreases. Then what does it indicates? What is the conclusion from this graph? This graph gives the conclusion from this graph between second virial coefficient by sigma by versus k by epsilon 0. The first one, it agrees reasonably that the behavior of certain gases like argon, nitrogen, neon, methane, where the intermolecular potential is spherically symmetric. Second one is, it is based on the potential well-shaped graph. Third conclusion is, the value of potential is much lower than 0. So B2T, which is the second virial coefficient, which is a function of temperature, is negative and expected at a low temperature. If temperature is high, you will find B2T tends toward positive, B2T becomes positive, and we see dominant interactions. And at extremely high temperature, you will find the hard sphere diameter ceases with increase in temperature, so B2T fall rapidly. So these are the conclusions that is obtained from your Lennard-Jones assumptions and a calculation of the virial coefficients. This is all about your unit 12, and next unit is cluster expansion for interacting systems. So we must know what is a cluster first. You know, cluster means one part, that means where the molecules, physical interaction between the molecules are possible in a cluster, in that cluster. And we found that the several manifestation or cluster diagrams can be done considering a large number of molecules. So in this chapter, we basically deal with the cluster integrals. What are cluster integrals? We have expressed in the last chapter the virial coefficients Bz in terms of partition function Zn. Now the task is the virial coefficients in the configuration integral, that is Bz, are called the cluster integral. Remember, the virial coefficients Bz are called here cluster integrals. So we have to consider the second virial theorem, virial coefficient, that is B2. the second virial coefficient B2 is minus B2, which is equal to minus 1 by 2V Z2 minus Z1 square. That is nothing but minus 1 by 2V Z2 minus Z1 square is written as your E minus beta phi 1 2, that is interaction between Lennard-Jones LJ potential into dq F1 bar into dq F2 bar. So we introduce the relative coordinates, and the relative coordinates, that is R is R2 minus R1 vector between distance between two molecules. If this is R1 and this is R2, then we can find this is R2 minus R1. So this term indicates B2 is equal to 1 minus 1 by 2V integration D3F1 into D3R1 integration D3R e to the power minus beta, which is a function of Lennard-Jones potential phi r minus 1, which is equal to minus 1 by 2 e to the power minus beta phi r minus 1 into 4 pi r square dr. So you can find the Lennard-Jones potential, that is gives the idea, the derivation of second virial coefficients. Now we use the third virial coefficient B23. This is B2 and this is B23. What is B2? B2 is 1 by 2V e to the power minus beta phi 1 2 minus 1 into D3 R1 bar into D3 R2 bar, which is half of e to the power beta phi 2 minus 1 D3 R1 2. Now we, after certain mathematical simplification, you will obtain this B2 is minus V e to the power minus beta phi 1 2 minus 1 dq R1 2 into e to the power minus beta phi 3 1 minus 1 d3 f3 1, which is nothing but 4V B2 square. And similarly, the third cluster integral Ci, third cluster integral, which is third virial coefficient, becomes 1 by 6V triple integration e to the power minus beta phi 1 2 e to the power minus beta phi 2 3 e to the power minus beta phi 3 1 minus e to the power beta phi 1 2 minus beta phi 2 3 minus beta phi 3 1 plus 2 into d3 r1 dq r2 into dq r3. So finally you obtain, simplify this, you will got this V3 is nothing but 1 by 3V triple integration e to the power minus beta interaction between first and second particle phi 1 2 minus 1. This is first, second and third particle. This is third and first particle. Same thing multiplied by dqr1 dqr2 into dq. You have to remember this V2 value and V3 value. 1 by 3V triple integration e to the power minus beta phi 1 2 minus 1 e to the power minus beta phi 2 3 minus 1 e to the power minus beta phi 3 1 minus 1. So what do you find? You find this V3 value and this V2 value, you will find they are exactly same. Just V2 represents in a two-dimensional coordinate and V3 represent in a three-dimensional coordinate. So what is the characteristics of virial theorem? Third virial coefficient V3. V3 represents, V3 make effective contributions to the molecular forces. It gives a effective contribution to the molecular forces. But V2 is a two-body effect. While V3 is a three-body effect, or V2 represent a doublet, then V3 will represent a triplet. We know we can define a function or involve a function Fij, that is interaction between ith and jth. Fij is e to the power minus phi 1 2 1 3 will be treated as minus phi ij by k beta t minus 1. And for a perfect gas, this phi ij is 0. So we can find this graph indicates if you plot the graph, this is the nature of the graph, how it varies with distance. You can compare if phi r versus r graph is plotted, this is the shape of the graph. And what is the conclusion? This conclusion suggests this f we have considered, fij, this represents a Mayer's function. And how can we define this Mayer's function? In order to define the Mayer's function, we have to consider this equation, that is e to the power minus beta is e to the power minus beta sum over phi ij, that is e to the power minus beta phi 1 2, phi 1 3, phi 2 3, and so on. And finally, we are able to obtain the expression that e to the power minus beta phi is 1 plus summation fij, plus next term will be interaction between, second term is interaction between I and j particle, third one is interaction between ij and kl. Similarly, you can say ij, kl, mn, then mn, op in this manner. E to the power minus beta phi is the first particle is 1, second one is between I and j fij, third one will be between ij and kl. Next, similarly, the expansion continues. And all these things can be put under cluster diagram. So in the cluster diagram, this is your cluster diagram. That means we consider these are the cluster diagram. If it is a two body, B2 represent two body effect, B3 represent three body effect. This is cluster diagram between two molecules, first molecule and second molecule, and the clusters is the integral represented over the terminology F12 between two molecules. So this is cluster diagram between triplet, that is F12, F23 and F31. You can have cluster diagram between 4 particles and 6 particles. If you consider this equation, which was, that is third virial equation, the third virial equation indicates that B3 is 1 by 3V triple integration F12, F13, F23, that is Fij you have defined the Mayer's function, into D3R1, DQR1, DQR2, DQR2. If we examine the integral of 3 particles, then we can say if Fij is 0, then Ij is separated by certain distance R12, R13 and R23. Then these 3 particles, 1, 2 and 3, they represent the integral which involves the cluster particle. You can see one end is not there, one end is open, and they are treated as a cluster diagram. This diagram has 3 topological equivalent cluster diagram of 3 particles which are singly connected. Now, our aim is to represent this cluster diagram in terms of 2 virial coefficients, that is B2 and B3. We know the result we can represent in one end, B2 and B3 can be written as Bj plus, that is minus j by j plus 1 Bj. What is Bj? Bj is 1 by jv integration over continuous range, sum of integrations, into S of j plus 1 dr1 dr2 drj plus 1, where S1 to j plus 1, the sum of all product of the functions are connected by the molecules. So this is called a double connected. Now we can draw these particles. Many examples can be done. Suppose the topological equivalent diagrams of these cluster points. Suppose we have 4 particles. We have 4 particles which represent on 4 sides of a square, first particle, second, third and fourth. These 4 points are vertices of a square, 1, 2, 3 and 4. This is one of the stars involving 4 particles, this diagram. And then now we can suggest this one can represent with three ways. It can be represented. One can be connected with 2, 3, 2, 4, and 3, 4. Similarly, you can connect 1 with 3, 4 means 2 with 3, 4 and 3 with 1, 2. So there are various combinations possible, and we can write the Mayer's number coefficient that is F12, F13, F34 and F this one. This is 1, 2, 3, 4. This is 1, 2, 3, 4. 1, 2, 3, 4. This is 1, 2, 3, 4. This is 1, 2. Various ways we can represent the diagram, the points 1, 2, 3, 4. And accordingly, we define the Mayer's constant, the Fij, as F12, F13, F23, and F24. So, for these four figures, what will be the cluster integrals? The cluster integrals can be denoted by this one, A, B, C, D. Either you can say this corresponds to A to D, A to C, and B to C, or you can say B corresponds to A, D, or C. These are the cluster diagrams in which we can represent them. So, if we, an example, let us consider an example. Let P denotes number of points. Points means number of particles. And K is number of lines joining. And M is number of topological equivalent graphs. So, for K is number of lines. What is number of lines? A single line, nature of the graph. If number of lines is 2, this can be represented by this one, and we have what is the tabular form is 3. Similarly, we can connect these 3 points by 3 lines. The top K is 3 means 3 lines, and this M is equal to 1, it represents one figure. In this manner, we can have large number of cluster diagrams. And the partition function, configuration integral, can be represented in terms of this partition function. Earlier we have derived. That is Z of n is the sum over integration, sum over continuous product, where I is less than j, 1 plus Mayer's coefficient Fij, dq3r1, dq3r2 for n up to n particles, dq3rn. Then you can replace this as 1 plus sum over Fij, sum over Fij, Fkl, as I have discussed earlier, up to this one. So, this Xa can be represented in this manner by 6 diagrams. 6, 1 to 2, 3 to 4, 5 to 6, 7 to 8. By this 1, 2 can be represented connected with the other 6. So, this is a 8 particle graph. In this manner, this can be represented. The new way we can express these 8 particles as this dq3, dq4, dq6, dq8, f12, dqr1, dqr2, f5 to 7, we have represented 5 to 7, dqr5 into dqr7. In this manner, with the topological diagram can be represented in your or in the cluster diagram can be represented. Now, the thing is, when n particle graph is a collection of, we conclude, n particle graph is a collection of n distinct circle numbered 1, 2, 3 and so on up to n, and the number of lines join the same number of distinct pairs. If the distinct pairs joined by lines are the pairs nu, lambda and so on, then the graph is represented by this one. You can write either 1, 2, 3 in this manner or 1, 2, 3 in this manner. 1, 2 and represented by 3. This is 2, 1 represented by 3 along this one. So these are called the diagrams, cluster diagrams. It can be possible, and the conclusion from this diagram is the configuration integral, which is represented as Jn, is equal to the conclusion from this graph is Zn is the sum of all distinct n particles of the graph. What is Zn? Configuration integral Zn, which earlier we told partition function, they corresponds to sum of distinct particles of the graph. Zl is the sum of the n particles of the graph. Let us focus on L cluster. What is L cluster? Suppose we have L cluster is L particles connected. We have L particles. We do not know what is L. This is 1, 2, 3, 4, 5, 6. So 1 connected to 3 is connected to 2, 1 is connected to 4, 4 is 6, 6 is connected to 5. So this cluster integral, say cluster diagram is nothing but this dq1, dq2, dq6 up to dq6 and f13. This is f14. This is f23. Passive interaction you can get. 1 interacts with 3, so Mayer's number f13. Interacts with 4, f14. But 1 does not interact with 2, so there is f12 term is not there. f24 term is not there. They do not interact. But 4 interacts with 6, so f46. 5 interacts with 6, so f56. 1 does not interact with 5, so f15 is not there. Hence, only lines which are connected, the Mayer's number came to those spheres which are connected by lines, the indices, the running indices 1 and 3, when 1 and 3 are connected, and correspondingly, your position that is dqr1, dqr2, they are. And the term we have defined, that is your first virial coefficient, can be obtained from this cluster integral as b1, which is a function of dt. You can calculate that is 1 by lambda to the power 3 L minus 1v, sum of all the possible L clusters. So, if we multiply a normalization factor, then we can study the characteristics of B1 Vt. B1 Vt is dimensionless. It is a finite number. And now we can represent the 3 virial coefficients. First one is B1 is 1 by V integration dqr1, whose value is 1, I have told earlier. B2 is 1 by 2 lambda q dqr1, r1 to f1. And B3 is 1 by 3 factorial 1 by lambda to the power 6v. So this is the integral and the sum of these integrals. There are general many ways to form this L cluster. You can form in this manner 1, 2, 3. You have L. How can you expand this cluster? Possible S. Then you can expand this cluster which was Z n Vt is D3 dqr one dqr two dqr n up to 1 plus f12 plus f13 so on. Then this qn Vt as 1 by as 1 by sum of condition, sum of continuous product 1 by n factorial v by lambda to vi function of Vt is 1 by this one v j Vt by lambda q to the power m 1 by m2 factorial v by aq z square b square to the power m square. So when you make a mathematical simplification, you will find the term under limiting condition v tends to infinity, p by kt is 1 by lambda q bij. So n by v is equal to 1 by lambda q, this one to the power z. And what conclusion we do? From cluster expansion equation, Mayer or formation is possible, and we can expand these virial coefficient and virial numbers. Now the question is, this is all about your second chapter, that is chapter 13. Now we will go to correlation and scattering. That is your chapter 14. Correlation and scattering, we will discuss the conceptual fluctuations. We know fluctuations, your electric line fluctuates, your energy fluctuates, number of particles fluctuates, pressure, temperature, all the variables undergo fluctuation. So, and as a simple mathematics, simple knowledge, what do we mean by fluctuation? Suppose we have x. X changes, fluctuates to x plus del x or delta x. So, delta x is the fluctuation. But in statistical mechanics, we mathematically, the fluctuation is represent of any physical parameter x is represented by delta x, which is x minus mean of x. We have seen in our first class what is mean, what is standard deviation, what is quotients, and all that is shown. So the mean fluctuation, that is x mean, the symbol x expectation. Since mean fluctuation can be written as delta x, x minus x mean of fluctuation, that is x fluctuation, x mean minus x mean, or x expectation minus x expectation, which is 0. Now we can take the standard mean square deviation. Mean is this, the mean square deviation, that is delta x fluctuation mean square. So delta x mean square, or you can say delta x square expectation, is equal to expectation of x minus x mean the square. When you take its square, this simple square form, and you can write this expectation x by mean of x into x is x expectation square. Then we can write delta x square expectation is the x square expectation minus x expectation square. So the mean square deviation provides a measure of strength of fluctuation, which is given by delta x square mean by x mean square to the power half. So this term becomes dimensionless when we multiply the term that is f. Hence, we can calculate, considering this equation, these two equations, we can calculate the fluctuations of different integrals. So, fluctuations of different ensembles. Our ensembles are known, that is canonical ensemble, microcanonical ensemble, and grand canonical ensemble. Our aim in this chapter is to calculate the fluctuations of canonical ensemble first. So we will use these equations, that is, we will start from this equation, fluctuation of delta x is equal to x minus x expectation. We should remember it in mind. And delta x square fluctuation, that is standard variation, is x square fluctuation minus x fluctuation square. Considering these two into account, we can find the fluctuations of canonical ensemble. So, a canonical ensemble is a representative system, is a consideration of a representative system in equilibrium. And the thermal equilibrium is represented by T, that is the exchange of energy, where the temperature Tv and temperature, volume, and number of particles remain constant, and the particles can exchange energy with the reservoir. When the particle exchange energy with the reservoir, temperature, volume, and number of particles are same, but energy is exchanged. Automatically there is a energy fluctuation, we say. Then how can we calculate energy fluctuation? For canonical ensemble, we know the fluctuation of energy is written as E square expectation, or E square fluctuation, or E square mean is sum over summation En square e to the power minus En by k beta t divided by e to the power minus En by k beta t. And we define a quantity Qn, that is e to the power minus beta in this one, where this beta is 1 by k beta t. Now the expression of this mean E and mean of E square can be written as mean E is 1 by Qn sum over En e to the power minus beta En, which is nothing but to 1. This is 1 minus 1 by Qn. This term En e to the power minus beta En, you can find if you differentiate this term. Differentiate Qn is our e to the power minus beta En. You differentiate this dQn with respect to beta. What you will obtain? You will obtain En minus En beta En. So this E, that is mean of energy, is minus 1 by Qn del Qn by del beta. And what is E square? Our n is E square average. E square mean is equal to 1 by Qn, that is summation En square minus beta. So before proceeding further, we will discuss these two equations. What is the first equation? We will take this example. What is E square average or E square mean? That is 1 by Qn in this manner. Del square, देखो E average is minus 1 by Qn del Qn by del beta. What is E square average? E square average is this one, but we will prove it is 1 by Qn del square Qn by del beta. And we can prove del E square is k beta t square Cv, where Cv is heat capacity of the material. Now, we are in a position to find the desired fluctuation. Now, what is our aim? Our aim is to calculate the desired fluctuation in a canonical ensemble. In a canonical ensemble, TVN remain constant. When energy changes, we can find the mean of energy E and mean of energy square. Mean of energy E is minus 1 by Qn, this one. Mean of energy square is this one. So to derive this one, we consider this equation and we find the fluctuation which is denoted by F, that is mean of delta E square by E square, mean of E square to the power half, which is equal to k beta t square Cv by E expectation square to the power half. This is a law of thermodynamics and valid only for small values of F. If F value is small, this law of thermodynamics holds good. So we can find the fluctuations for a perfect gas with respect to its energy and space. Rho, expectation of rho is 1 by Qn Pi e to the power minus Ei by k beta t, where Pi is equal to minus del Ei by del V, and the expectation of P into Qn is equal to del Ei by del V e to the power minus Ei by. Take the partial derivative and you will find the mean value, the mean fluctuation value, that is del P square mean is k beta t del Pi by del V plus. We have to evaluate del square E by del V square for a perfect gas by using this equation. So, what is the fluctuation of a canonical ensemble? The fluctuation of a canonical ensemble is calculated by equation del P square expectation is 1 by k beta t del p by del v plus expectation of del square E by del V square. So we evaluate del square E by del V square for a perfect gas, and then we can find what is the fluctuation of a canonical ensemble. Similarly, the next heading is fluctuations of a grand canonical ensemble can be calculated. The fluctuations of grand canonical ensemble depends on number of particles, and it also depends on the exchange of mass with the reservoir because it deals with the chemical potential. In order to calculate the fluctuation of grand canonical ensemble, we have to calculate whenever there is a mass transfer, we have to calculate the density fluctuations. And the density fluctuation rho varies as n to the power minus half. So under ordinary condition, the value of n is 10 to the power 22. But the fluctuations are of the order of 10 to the power minus 11, which is negligible. So fluctuations in grand canonical ensemble is very less, and it has an isothermal compressibility which becomes infinitely large at the critical point. So we have to calculate the density fluctuations, which gives rise to large scale scattering of light, which is a phenomenon of critical opalescence of light. So in scattering of light condition or the critical opalescence of light, we can calculate the fluctuations that is for grand canonical ensemble. Similarly, we can calculate fluctuations for microcanonical ensemble. We know in a microcanonical ensemble, what remains constant? Energy, volume, and number of EVN. Energy, volume, and number of particles remains constant. So the probability is developed by the Einstein's suggestion that non-equilibrium of entropy is possible. So the non-equilibrium entropy of expansion is given by the canonical partition functions. Both the grand canonical ensemble and microcanonical ensemble are avoided in mathematical calculations. Remember, only we have calculated the fluctuations for canonical ensemble, but we have not taken calculations of microcanonical ensemble and grand canonical ensemble because of these reasons. In canonical ensemble, the fluctuation which was calculated was very small. That means if ordinary collision number is of the order of 10 to the power 22, the fluctuation is of the order of 10 to the power minus 11. But here the fluctuation is of the order of 10 to the power minus 10 to the very less. So we ignore those fluctuations in quantum mechanics. Then we will define a correlation function. What is a correlation function and why correlation arises? To study the relevant situation in statistical mechanics, we need correlation function. Let us have what is the relevant situation. Let us explain with an example. Let we have n number of particles, and the position vectors are r1, r2, that is represented by ri. So using Dirac delta function, we can write n of r is the summation I is equal to 1 to n delta q r minus ri. Here 3 is not any power, and the subscript I which runs from, that is a running index from 1 to n, has three spatial components along x, y, and z direction. And the number of particles, which is a function of r, is a time dependent function. But when the system is in equilibrium, it can be noted that each delta function gives some contribution to the particle. So we must define the correlation function first. So what is correlation function? the in order to resolve the issue of simple systems having only two particles. Suppose we have a simple system consisting of two particles. So we fix one particle of the system and it indicates the relevant position of two particles. So we define the position of two particles at a distance r and r dash, and a corresponding the density function is represented by nr and nr dash. Then the average product of density function can be maximum under which condition? You can see there are two functions at a distance r and r dash, and the average of this density function can be maximum provided the mod of r and r dash is equal to rg. So we have a quantity, this nr dash, this represents the pair correlation function or correlation function. This is because of two particles, this is called pair correlation function or correlation function, which is defined by this manner. G for two particles are at a position distance r and r dash, G r dash is average of nr minus mean of nr into average of nr dash minus mean of nr. This is according to fluctuation. Otherwise, we can write G r minus r dash is n average of nr dash minus n square. When you define the correlation function by this equation, then what will be the shape of correlation function? The shape of correlation function can be represented by Dirac delta function, that is n average of nr dash, this correlation function is equal to sum over I runs from 1 to n, sum over j runs from 1 to n, delta q r minus Dirac delta function delta q of r minus ri into delta q of r minus rj. So RHS have two kinds of function. One is for I and other is for j. And these are two Dirac delta functions, and we know product of two Dirac delta functions is equal to 0. So that can be written as delta of the three dimension Dirac delta function, delta of r minus ri and delta r dash minus rj is k times k is a numerical constant, delta of r minus r dash. As a result of this, we are able to calculate that this correlation function can take the shape with considering n is number of particles per unit volume as correlation from G r minus r dash n delta q r minus r dash into n square gamma. This is a gamma function, gamma of r minus r dash, where gamma is a dimensionless function. So the Fourier transform of this function is written as f of k, the integration dqr e to the power ikr f of f, and g of k is n plus n square gamma k, where gamma k, that is the your Fourier transformation of this function, can be written as written in this manner, and gk takes the form n plus n square gamma k. This gamma k has this form, that is ck plus n ck bar into gamma k. This is the Fourier transform coefficient we say, and the gk can be written as in the form 1 by n minus c bar k. In which condition, if we consider the Fourier reverse transformation, then we can have this function. So what is the physical significance of this correlation function? The correlation function can be written in this manner. If we consider a homogeneous isotropic classical gas where potential energy arises from two body interactions, then we can write W is equal to sum over I and sum over j phi of Ri minus Rj mod. So the correlation function can be written as 2 pi n 0 to infinity dqr r square gamma r phi. Now the correlation function indicates the are correlated with the thermodynamical quantities, and that can be written as n minus expectation n square is kt v n square k beta. So from taking this expression or using this expression in the correlation function, we can find that correlation function can be linked with any temperature and it defines the isothermal compressibility of a system. It can be for a fluid, it describes the scattering phenomena. It also explains scattering phenomena in electromagnetic radiation. Now, what is the relation between correlation function and scattering? The correlation function, let us have a plane electromagnetic wave, which is characterized by the wave vector k. So the intensity of scattered wave, there is a scattering, the k is the initial vector, wave vector, and after scattering it goes to another wave, that is k dash. So k minus k dash, k minus bold k, that is k is your wave vector and k dash scattered wave is k minus k, such that the amplitude of ith particle is represented by its intensity of Ik is summation AK square. We know the intensity of a scattered wave is directly proportional to square of its amplitude. In the same thing with notations, this AIK is the amplitude part. This IK represents your intensity. For n number of particles, the intensity of scattered wave is the amplitude part square for nth particle. So this AIK can be represented as a simple scattered wave form, that is AIK is A0 e to the power Ik, where A0 is independent of the particle position. Now the intensity term is, if when you multiply, this is A0 square e to the power IKR, this is a simple plane progressive wave into e to the power minus IKR. So this is A0 square, summation I is 1 to n, summation j is 1 to n, e to the power Ik Ri minus Rj, and the average of this. Here, the quantity in this bracket, this term, summation I runs from 1 to n, summation j runs from 1 to n, e to the power Ik Ri minus Rj, you have read in your solid state physics that this represents a structure factor. And this structure factor can be a static structure factor. In this condition, we can write for n particle system, this static structure factor S, which is a function of k, can be written as 1 by n, summation L is 1 to n, summation j is 1 to n, e to the power Ik Ri minus R. Hence, we can write the total intensity as sum over A0 square, initial maximum amplitude, and integration over dqr dash e to the power Ik R minus R dash NR into N. Then we can say how it is related with thermodynamical variables. It is, we know the internal energy of a system, U is equal to, say, for monoatomic gas is 3 by 2 n k beta T. N is number of particles, k beta is Boltzmann's constant, T is equal to absolute temperature. So in order to make a relation with thermodynamic variables, we can find the relation looks like here, looks like in the following shape, that is E is equal to 3 by 2 n k beta the total energy plus due to this correlation factor and structure factor, this is NP phi r GR 2 pi square. When you consider these expressions, we can find the correlation and scatterings are related with each other, and fluctuations plays a vital role in converting this scattering phenomenon. So scattering phenomenon plays a vital role during the transition, during a calculation of the correlation functions and scattering functions. This is due to the fluctuations. And next one is our phase transition. We know different solids. In the next chapter is phase transition. In this chapter, we will focus upon what is phase transition. Second heading is what is mathematical definition of phase transition. Then phase diagrams of pure substances, isotherms, and real gases. Then we will use some mathematics for first order phase transition. We will discuss Clausius-Clapeyron equation of phase which arises due to phase transition. Then we will derive second latent heat equation. Then we will focus on mathematics for second order phase transition, Ehrenfest equation. Then we will define what is cooperative phase transition. In our, we know phase transition is possible when water goes to steam or ice becomes water or solid sulfur gets vaporized sulfur or solid vapor transition. So in this manner, various phase transitions are possible, we have read. That means solid can be converted to liquid, liquid can be converted to gas, and solid can be converted to gas and vice versa. That is fusion, vaporization, so many in this manner, sublimation, so many phase transitions are possible. And we have read those phase transitions. For these phase transitions, we consider the differential calculus here, which makes a bridge between mathematics and our understanding on phase transition. Remember, phase transitions are based on symmetry and order of differentiation. The first order derivative of Gibbs potential, when changes discontinuously during the process, remember, when first order derivative of Gibbs potential changes discontinuously, we get first order phase transition. And when second order derivative changes discontinuously, then we get second order phase transition. So we derive from this one, when you know first order and second order phase transition, we are able to derive the latent heat equation and Ehrenfest's theorem. And we know from the last chapter, the correlation and scattering, that this is a cooperative phenomena of interacting system. So we will focus on the due to interaction, they are also a phase transition. And that is expected, that is explained by your Ising model. And that is phase, second order phase transition, which will be discussed in the next chapter. And the most important theory, that is Ising model, which deals with the magnetic phase transitions, will be discussed. So now we will say what is phase transition. I have told you that the term phase transition is largely used to describe changes from one state to other state of matter, that is solid to liquid or liquid to gas, and some rare cases or solid to gas, or in rare cases to plasma. So every element or substance undergoes phase transition under specific conditions of temperature and pressure. So the route of phase transition is traced by intermolecular interactions. And this example, suppose we have to take an example. Let us convert 1 gram of water to 1 gram of steam at 100 degrees centigrade. And by using first law of thermodynamics, we can calculate its internal energy. So when we go from 1 gram of water liquid to 1 gram of steam at 100 degree, we have to 1 gram of water at say 0 degree, we have to calculate from 1 gram of water 0 to water 100 degree, the amount of heat required. Then from 100 degree, 1 gram of water 100 degree to 1 gram of steam 100 degree, there is a phase transition. So that is from liquid to vapor. The phenomenon is vaporization, and the phase transition takes place. So this mathematically, this is explained by first law of thermodynamics. If you consider this one, then you can find, take the help of the equation dq is equal to du plus pdv. And from going from phase transition 1 gram of water at 100 degree centigrade to steam at 100 degree centigrade, what is the amount of heat required? We require 540 of heat. So this is called latent heat of vaporization. Similarly, 80 calorie if 1 gram of ice is converted to 1 gram of water at 0 degree centigrade, the latent heat of fusion of ice becomes equal to 80 calorie. Hence, if we have done some mathematical calculations, how we can calculate the total amount of heat required during the conversion of certain substance from one state to other, and in between, suppose we go from ice state to vapor state, we come across two phase transitions. One is from solid to liquid, that is ice 0 to water 0, whatever the amount may be. The other one is water 100 to steam 100. In two phase transitions occurs. So, in order to understand that, let us have some mathematics on phase transition. Let us recall our equation, this equation. We will define some equation, certain terms. Our Helmholtz free energy, Gibbs potential, and Gibbs potential is a Helmholtz free energy. Then we can recall our equation. U is internal energy, S is your T is temperature, S is your entropy. So you know these two equations. A is U minus Ts, and G is equal to U plus PV minus Ts. Now, the thermodynamic system, you can differentiate this. dA is du minus Tds minus SdT. So, du plus Pdv is equal to Tds, simple thermodynamics, and du minus Tds is minus Pdv. If you put this value here, dA, du minus Tds is minus Pdv, dA which is equal to Gibbs potential, Helmholtz free energy, A, that is del A by del T, Helmholtz free energy, and Gibbs potential G, they are related. Del A by del T is equal to minus S entropy, and del L by del V is equal to P. So, for a reversible infinitesimal process, you find the is equal to minus V change in this potential minus VdP minus SdT. From this one, we can obtain the first derivative of Gibbs potential. Hence, what is first? If any higher order does not exist for certain values or parameters which fix the system, we conclude the system undergoes phase transition. Remember, when phase transition occurs mathematically? Now, if higher order derivative does not exist for certain values or parameters which fix the system, we conclude that the system has phase transition. So we say that du, the change in internal energy, we can write in this manner, that is TdS plus HdM, where dm is your volume. We can change this parameter PdV can be written as V changes to M and P changes to H. So the expression M is your magnetic system and V stands for mechanical system. M stands for magnetic system, V stands for mechanical system. So the expression for potentials, that is homogeneity and this one, A, which is a function of T, and X is the extensive variable, because it will lead to classify our phase transition. So the classification, phase transition classification, may be first order phase transition or second order phase transition. That means phase transition depends on the order of transition. So we have a familiar example, that is liquid vapor phase transition. Here there is a discontinuity in the first order derivative. When there is a discontinuity in the first order derivative, we say this is our first order phase transition. That means the second order does not exist. Similarly, when discontinuity arises in the second order derivative, then that is your second order phase transition. And in this case, the latent heat plays a twofold role. That it plays a twofold role, which can be obtained by this equation. You see, there is a question we can ask ourselves: does phase transition in magnetic system require a latent heat? And if required, what is the expression? We know from above equation that from this equation we know dg by dt. These equations we can consider dg by dt, which is equal to minus s. If you consider this equation, then we can find del by del t of del g by del t. Del g by del t is s, so del by del t of del g by del t is minus del s by del t. This can be written as minus 1 by, this is del square g by del t square, that is minus 1 by t into multiply t and divide t. So this is nothing but your Cp, that is specific heat at constant pressure. And specific heat at constant pressure indicates Cp is equal to del square g by del t square is minus Cp by t. So this indicates that mathematically we can find phase transition in magnetic systems. If you look the graph, this is the graph for first order phase transition. First order phase transition, here first derivative, in case of phase transition, the first derivative is continuous, but higher derivative is not there, then it is said to be continuous phase transition. If first order derivative is discontinuous, then This is called first order phase transition, which is discontinuous in nature. So if this is gives potential G, this is entropy, this is temperature, then you can say how this G varies with S and G varies with T. This is for first order phase transition, variation of G with T, and this dotted line represent variation of S, variation of G with S. G with S variation, and this is G with T variation. This is for discontinuity phase, discontinuous phase, and this is for continuous variation of phase transition. Here, the vertical dotted line represent a transition phase temperature. Here, this line is the transition phase temperature. This is the temperature, this is the entropy, and this is Gibbs potential. This indicates that the variations, the continuous variations, and the discrete variation in first order phase transition, and continuous phase transitions undergo the different manner. They never run in same manner. Now, the phase transitions can be described in terms of symmetry. That means, what is symmetry? The symmetry and what is its role in phase transition? We know in case of liquid as well as gas, phase transition undergoes isotropic. So in each phase, there is a rotational symmetry. So liquid gas transition, in liquid gas transition, there is no change in symmetry of the system. And this symmetry is also found in paramagnetic and ferromagnetic materials. Materials we will discuss in case of second order phase transitions. So what is phase diagram of a pure substance? As per our plus 2 knowledge, we know if this is pressure, this is temperature, a substance, this T is your triple point, this S is the solid state, L is the liquid state, and this is gaseous state G. So this when phase transition takes place from solid to liquid, this line is called ice line. This is pressure, this is temperature. When temperature increases, solid is converted to liquid, this line is called ice line. And further increase in temperature, liquid converted to gas, this is called steam line. And when solid directly converted to gas, this is called hoarfrost line. And this point T is called the triple point 273.1 Kelvin, which is called triple point, and where three phases, that is solid, liquid, and gas coexist at this triple point. So this phase diagram for a pure substance looks like this. But when you consider the phase diagram condition of certain substances, we say at the triple point, does the triple point exist? Is it physically exists? In order to get the answer, we consider an isothermal system. That means if T is temperature, del T, isothermally del T is equal to 0. And for isobaric process, del P is equal to 0. And for other systems besides these two, dg is equal to 0. And we can say if we have a fusion case, say solid goes to liquid or liquid goes to gas. When solid goes to liquid, the Gs, that is gives solid having potential, is GL. When it goes to liquid to gas, GL is GG, and when it goes to solid to gas, GS is GG. So we define this by means of a parameter, by means of an equation, that is, say S1 is equal of the two curves, S1 plus lambda S2 is 0, where lambda is the arbitrary constant. So GS minus GL is 0, GL minus GG is 0, or GS minus GL plus lambda GL minus GG is 0. considering these aspects of phase transition, we can draw the graphs for a real gas. We know the Van der Waals gas condition. We have drawn the PV diagram. This is P by Pc versus V by Vc. This is Van der Waals isotherm for various temperatures, and we have discussed this. The isotherms corresponds to critical temperature, critical pressure, and critical volume, and this gives rise to Van der Waals equation. But we have to understand why del P by del T is negative here during this graph. If you study this graph, the del P by del T term is negative, the slope is negative. It indicates that it attains critical temperature over a wide range of value of T and Tc. When slope is 0, we find that all the points corresponding either minima or maxima. At minima, del square P by del V square is 0, and max is greater than 0. At minima, del square P by del V square is greater than 0, and maxima, del square P by del V square is less than 0. And C represents the critical point. When del square P by del V square is 0, this is critical point. So this is the critical point, and A is minimum. This A is minimum when it is greater than 0. A is maximum. B is maximum when this is less than 0. So this point is called the first and second derivative vanish, and this is called, when it is 0, the first and second derivative vanish, and this is called point of inflection. Now we will discuss what is mathematics of first order phase transition. We know the Helmholtz free energy is A and Gibbs potential is G. Then dA is minus VdV minus SdT. dG is minus VdP minus SdT. As a result, we obtain del A by del T is minus S, del A by del V is minus C. When you and del G by del P is minus V, and del G by del T is minus S. What does these four equations indicate? This indicates the entropy changes discontinuously, volume changes function of pressure and a transition point. So we get a isotherm where dt is equal to 0. Where T is constant, dt is equal to 0, and dg is equal to 0. So this graph indicates that these are the graphs drawn from G versus T, entropy versus temperature, volume versus temperature, and this gives rise to famous Clausius-Clapeyron equation. The Clausius-Clapeyron equation uses theoretically in Maxwell's thermodynamic relations. From those four Maxwell thermodynamic relations, you take the third equation, you can derive this one, this Clausius-Clapeyron equation. And what is that? If P is dP is change in temperature with time, then and L is the latent heat, then if volume expands from V1 to V2, then Clausius equation can be represented del P by del T is S2 minus S1 change in entropy by change in volume, and during phase transition T remains invariant, so S2 minus S1 by S1 is L by T, hence dP by dt is L by T into dP by dt. From this equation you can describe the phase transition, that is when solid changes to liquid or liquid changes to gas, and temperature becomes greater or temperature becomes less. Two conditions you can derive. Similarly, we can reach at another conclusion. Equation, second order latent heat equation can be derived, that is S2 minus S1 is L by T. So what is d dt of L by T? That is ds2 by dt minus ds1 by dt. So dL by dt is equal to L by T C2 saturation minus C1 saturation, that is second order heat equation. So these are specific heat equations. This equation, specific heat equation, is the amount of heat required to raise the temperature of unit mass of substance. And this happens when the temperature of saturated vapor increases. So this is a second order latent heat. What does it indicate? The amount of heat required to raise unit mass of a substance of a saturated vapor is through 1 degree at 1 degree centigrade is called specific heat of a saturated vapor. Under this condition, we can say during phase transition what happens. During phase transition, what are the mathematical equations? We get differential equations. By solving those differential equations, we can obtain the first order phase transition whose discontinuity arises at certain point. Then how the second order phase transition takes place. When you consider Gibbs potential, there is a finite change in entropy and finite change in volume at a transition temperature. But in particular cases like liquid helium, during phase transition, the Gibbs potential, entropy and volume, they remain constant. But there is a discontinuity they are discontinuous, and second order derivative exhibits this discontinuity. At the transition temperature, the entropy remains constant and the latent heat is zero. In other words, if we consider the Clausius-Clapeyron equation, that is dp by dt is equal to L by T into T2 minus T1, then this becomes indeterministic because this is 0 by 0 form, something by 0 is infinite. So we will take this equation into account, and when you draw the graph between Gibbs function versus temperature, Gibbs function versus pressure, it looks like this shape. So this is a graphical representation of second order phase transition. Second order phase transition, this is G versus T, entropy versus T, volume versus T, specific heat versus T. This is a second order phase transition, and it also indicates the variation of shape quantities with pressure. This is variation with temperature, these graphs, variation with temperature, variation of your G, S, V and Cp with temperature. This is how variation of pressure with temperature. So these graphs, when you look, it indicates that we can derive certain new equations from the behavior of the graph. And one of them is this. For deriving Clausius-Clapeyron equation, we consider the continuity of Gibbs potential, and we assume a specific continuity condition of first derivative. So let us consider a specific entropy, and the entropy, say the entropy of these two gases are S1 and S2, and they are same, S1 is equal to S2. When they changes, S1 changes to S1 plus ds1, S2 changes to S2 plus ds2, then ds1 is equal to ds2. So we can say S1 is equal to S2, ds1 is equal to ds2. Now ds can be represented as ds by dt into dt plus ds by dp into dp. In this case, so you got the equation ds is cp by t into dv dt, dv by dt into dp. In this manner, when you proceed, you will calculate the first Ehrenfest theorem. You put here alpha is 1 by v del v by del t. So ds1 is equal to cp1 by t dt, v alpha 1 dp. Similarly, ds2 is this one. Since ds1 is ds2, so this equation is this one. You equate these two and you obtain the expression dp by dt is cp2 minus cp1 by t by v into alpha 2 minus alpha. So this equation is possible, and similarly other equations can be obtained considering the phase transition mathematics. Then what is cooperative phase transition? For weakly interacting systems, we find the contributions made by the individual particles expresses the partition function of the system as product of single partition function. So the interaction, but in case of strong interactions, the process decomposes easily. So for weak interaction and strong interactions, the phase transitions are different. How different? In a strong interaction, the thermal excitation takes place. Due to thermal excitation, there is a mutual cooperation among the substances. And due to mutual cooperation, the cooperative interaction takes place. This is all about phase transition 1. Next one is phase transition 2, where what is second phase transition 2? Here we will discuss Ising model. The Ising model is discussed with respect to magnetic fields. So what is Ising model? We know Heisenberg exchange interaction model. This is also called Heisenberg's exchange interaction model. And this is used for ferromagnetic materials. This interaction can be extended to neighboring lattice because the exchange energy arises from consequence of Pauli exclusion principle, and it turns significantly to the atoms almost in all directions. But Heisenberg purposed, if we have two ions I and J, and Si and Sj are two spins, then Ising model take help of Heisenberg's assumption. So he considered the certain terms that will exchange in characteristic exchange, and given by E exchange is 2J Si dot Sj, where J is called exchange integral. Remember, if two spins are Si and Sj, then Heisenberg suggested the energy exchange between two ions having two spins Si and Sj for ferromagnetic substances are E exchange is minus 2J Si Sj. So the consequence of overlapping of these charge distributions indicate the problem that this term minus 2J Sij into minus Sjz is the prevalent term in the one-dimensional model. So we consider one-dimensional Ising model. Our prime task is to set up the Hamiltonian first. So for ith particle having n number of such spin, the Hamiltonian H is minus H summation I is equal to n Si minus J summation Si into Sj. So we create a situation where Si takes integral values. That means the first term minus H summation I is 1 to n Si has twice the projection of spin in the direction of magnetic field. So what is the permissible value of Si? The permissible value of Si twice means plus 1 and minus 1. So the first term, that is H is equal to H, summation runs from I is 1 to n, Si minus J Si Si plus 1. The first term represents the external magnetic field, that is H factor H. H is half mu 0 is magnetic moment, and H is external magnetic field here, and small h is your Planck's constant. Hence, this first order Ising model. Now, question is why there is a factor half? In order to explain this term half, we have to consider the second term, that is Si plus 1. So it indicates that there is an interaction between two terms. Due to interaction, we consider the result gets half. So we take this one as h is equal to half mu 0 h. Now the question is, if we consider a large number of points, then what will be the relation for S n plus 1, where n stands for large number of points? In that case, there will be a perturbation method will be used because there are large number of particles. So we can write the commutating operator. In this case, we take help of a commutative operator to explain the Hamiltonian. So the Hamiltonian can be written as h is h0 plus h1, where h0 is minus h sum over I runs from 1 to n si, and h1 is minus j si s j I plus 1. So h0 does not contain any interaction. And this q, which is a partition function, this partition function takes the shape, that is q is equal to s, q0 is s runs from plus 1 or minus 1 e to the power beta hs. That means q0 is equal to e to the power plus beta hs plus e to the power minus beta hs. Or you can say this is nothing but hyperbolic function cos hyperbolic beta h. So the unperturbed partition function, that is z0 is q0 n 2 cos hyperbolic beta h to the power n, and si0 is tan beta hyperbolic beta h. Therefore si sj mean at state 0 is equal to si0 into sj0 for I is not equal to 0. So corresponding Hamiltonian h1, this factor h1, which is j interaction term, I is equal to 1 to n, si plus 1, h1 is j si1 in 0 state, and minus jn s1 s2 0, that is minus jn. What is s1 s2? That is equal to tan term here, tan beta h. So square, this is si0 into si0 into tan hyperbolic square beta h. And this leads to the second order perturbation term, that is h1 square. This is equal to 0 at j is equal to 1 is si square si plus 1 square. Since each si is plus or minus 1, si square will be. So h1 square 0 at I is equal to j. Now the term is, what is hi square average at state 0 for j is equal to I plus 1. The term within this summation sign si plus 1 square is 1 indicates this si plus 2 state at 0 state is equal to si 0 state into si plus 2 average 0 state summon tan hyperbolic square beta h. So we can consider the transition from one phase system to other phase system, and finally the Hamiltonian takes this shape. At state 0, hi average, hi square average is j square into n plus 2n tan hyperbolic square beta h plus n square minus 3n tan hyperbolic square to the power 4 beta h. So log z takes this. And considering this model, when we find there is a transition, we are able to solve the energy of the system comes around E is equal to minus del ln z by d beta, which is equal to minus n beta j, where E is a negative term. Since energy is negative, we can get an indication that ferromagnetism using Ising model, the solution is possible. This is also possible by considering the variational principle, When you derive Ising model from the variational principle, this indicates that the ferromagnetism transition below critical temperature is also possible. Directly we can solve it. Directly we can solve this one, that is a solution by direct method you can obtain. You choose one Hamiltonian. Write the Hamiltonian, h is minus h by 2 summation I is 1 to this one si sj plus 1 minus j si sj plus 1. Then you consider whether it is symmetric condition si is equal to si plus 1. Then you find its partition function z is equal to sum over continuous product summation beta h by 2 si plus 1 plus beta j si plus 1. This is interactive term, and si is equal to plus 1 forms a ket 1 0. Si is minus of 1 forms that is 0 1. When you choose to adopt this method, you get a Pauli-Steel matrix delta z 1 0 0 minus. So, in the more elegant way, you can say Sk is the matrix Sk sigma z Sk, and you calculate the trace of this matrix. The trace gives this transfer matrix. Transfer matrix gives e to the power beta h plus beta j, e to the power minus beta j, minus beta h plus beta h. So, the partition function, considering this transfer matrix, is equal to this one sum over s s1 tr s2 s2 tr s3 and so on, and the trace becomes this one 1 0 0. So when you determine this one, you can able to see that the phase transition occurs, and in case of, and the Ising model, first order Ising model gives an idea about when h is equal to 0, the magnetization is 0. That means the magnetization is 0 at all temperatures, because we have a factor here. Magnetization is n mu 0 by 2 sine hyperbolic beta s by this factor. So when sine hyperbolic beta s is 0, m is equal to 0, that means are all temperatures, because when h is equal to 0, it contradicts the result obtained using variational principle. So, variational principle gives an indication about spontaneous zero external magnetic field magnetization below critical temperature. And we find the mean field approximation led to the similar result. So, we will go to the second and third Ising model. So, in order to go to second and third Ising model, we consider this Hamiltonian. For multidimensional array of spins, the Hamiltonian is written as h is minus h summation I is 1 to n si square minus j si minus sj square. So, multidimensional model, you consider this, and what you will obtain? You will find that when you consider such multidimensional model, the second term in this model is a interacting term between ith and jth spin, and the I and j spin, it takes a form which confirms that x I square will be take an integral value. So the z component will be dropped, and we get the result for the Hamiltonian. Now we will consider one Bragg-Williams approximation. What is that approximation? We know the coordinate number in case of one-dimensional lattice, say q is equal to 2. We define R as the average spin and per site. Then we can write the average spin per site is S, which is the average 1 by n times Si to the power this one. And the term becomes, this one is minus NHR, where we have not bothered about the approximation. The second term introduces an approximation called Bragg-Williams approximation. So it is written by Hamiltonian is written as Hamilton-Bragg-Wiener application by considering this one. And the form of Hamilton, which you are considering in the Ising model, second Ising model, this term, second term, this takes this shape, that is HBW is minus H, I is equal to 1 to N, Sij minus J, this term is equal to sum over Ij, SS. And it gives rise to the energy ER is minus NHR minus half NQJR square. So this is about the Hamiltonian of second and higher order transition, whose canonical partition function Z is e to the power minus beta epsilon r. When we use this, becomes Z is equal to sum over r m by n by 2 1 plus r, n by 2 1 minus r e to the power beta n into this. So this is all about the phase transitions in second order. Next one is what is mean field approximation. Mean field approximation, you know from the VW approximation that we define the mean value of spin. But here we consider the it in a better manner, the field values can be approximated. So the Hamiltonian takes this shape minus H SI minus J by 2 SI SJ. But I extend all J in the and after arising second up is due to double counting. It also enables to write the Hamiltonian in this form, that H is equal to sum over I HI, which gives HI is equal to minus HS JS1 by S1. So writing in this manner, we got a result that the Hamiltonian can be expressed in this manner: H plus Q HMF. What is HMF? HMF is the mean field Hamiltonian, and a mean field Hamiltonian is finally J by 2 tan hyperbolic of this. And value of H is HE minus QJ by 2 tan hyperbolic. So mean field approximation is possible. We can also define the order parameter, that is G, which is obeys the elements of this group G, obeys G H G inverse is equal to G. G is treated as the order parameter. The critical exponents can also be defined, and critical exponents are defined by F, which suggests the condition. Under this condition we can have critical exponents, that is limit log fx by log x extends to 0 is equal to lambda. So we have discussed today about various type of transitions, and there is another model, Landau model for phase transition. What it tells? The Landau model tells that we can identify the order parameter worrying about the macroscopic phenomena. So Landau suggested we can restrict our discussion to magnetic phase transition, that the magnetization whose value is 0 represents disorder transition. Here our focus will be on critical temperature where M is small. Landau suggested the free energy can be expressed as a power series of M, that is A is equal to a constant term plus AM square plus BM4 plus this is a power series of M. The free energy, Helmholtz free energy A, can be expressed as a constant term plus AM square plus BM4 plus order of M to the power 6 and so on. When Landau suggested this, he got the equation like this one, that M0 is equal to 0, M0 can be plus or minus root 2 over A by 2B, and AT, the transition occurs at when A changes its sign. That means A finally A comes around, the constant is K0 plus A1 M0 square B0 M04. If you plot the graph, this type of graph will arise, and there are two minima located at M0. For this is for various power series, for various coefficients, and which varies with tau. There are two minimum values of M0, and we find that and in all these cases, the phase transitions are dependent possible in case of magnetic substances. So this is all about our discussion. Thank you for your patience. Any questions? If not, thank you.